Hi everyone, my name is Kamala Vasan and I am a PhD student at Department of Computer Science, University of Warwick. Today I am going to talk about our recent research on high-level FPGA accelerator design for structured mesh-based numerical applications. This is a joint work with my supervisor Gihan from Warwick, together with Isfan Reguli from PPCU Hungary and Suhaib Fahmi from Host, Saudi Arabia. The aim of this work is to study suitability of SYCL to implement a specific class of HPC application, structured mesh-based numerical solvers on FPGAs. Several works have studied the suitability of FPGAs for a number of areas and has demonstrated the key advantage in using them. Domains include deep neural networks. Bing and Baidu search engines utilize FPGA accelerators. FPGAs are also widely used in financial computing and domain-related databases. FPGAs have also gained traction for implementing high-performance parallel algorithms, particularly due to their energy efficiency compared to traditional processors, low latency in processing, and reconfigurability compared to ASIC-based accelerators are also attractive features. In recent years, powerful FPGAs have appeared in the market, including hardware with high bandwidth memory and native support for single precision operations on FPGAs. Additionally, cloud-based FPGA nodes have been made available, reducing the time required to set up the device and their maintenance. Along with these developments, FPGA vendors offers high-level synthesis tools, which drastically reduces the development time compared to low-level HDL-based design development. FPGAs consist of circuit elements such as adaptive logic modules, which includes lookup tables and registers, smaller RAM memories such as 640-bit MLAPs and M20K, dealer signal processing blocks, and routing fabric to connect these circuit elements. These circuit elements are used to create a circuit to execute certain algorithm or applications. The diagram shows the high-level architecture for Intel PAC D5005 accelerator card. Here some additional hardened modules such as DDR4 memory controller and PCIe controller can be seen in this Stratus 10 FPGA. Big DDR4 memories and network interfaces and PCIe interface can be found in this FPGA card. Kernels of an application designed by user will be loaded in this partial reconfiguration of FPGA. Challenge is how to effectively map an application or algorithm to the circuit. Since there is no fixed inbuilt architecture, even with high-level language-based synthesis, user must build memory hierarchy and take care of data flow, balancing the throughput. Other challenges are: 1. Larger reconfiguration time. Loading new set of kernels is costly on FPGA as it will take few seconds. 2. HLS tools are evolving, therefore debugging is considerably harder compared to traditional architectures. The work we did for this paper for IWOCL and SYCLcon are based on two previous work which we did based on silence FPGAs targeting the structured mesh application class. The first one was published last year at the IPDPS 2021 and it developed a generalized workflow for synthesis of near-optimal FPGA designs for structured mesh-based explicit numerical solvers. Basically, stencil applications including larger, more realistic applications with multiple stencil lobes. The second work, which will be published in ICS 2022, looks at implicit solvers, specifically multidimensional tridiagonal system solvers for FPGA. Our work for this IWOCL workshop extends these works, investigating the same designs for these application classes using SYCL and developing designs for Intel FPGAs. Our aim is to investigate how best to codify our designs using SYCL and overcome challenges in gaining near optimal performance with it. The two key challenges leading to the specific SYCL optimization are: firstly, on reducing kernel overhead by moving the iterative loop to the FPGA, and secondly, reducing the on-chip memory consumption by decoupling Thomas forward loop computation for the implicit applications. Our designs and workflow is applied to implement two non-trivial applications using SYCL. We used to showcase the performance of the designs on Intel D5005 FPGA. To give you a sense of performance from this FPGA compared to best traditional architecture performance, we compare the same application on NVIDIA V100 GPU using best implementation on the GPU, which are CUDA based. Research shows that competitive performance with significant energy saving on FPGAs. We analyzed the performance and present a number of lessons learned as part of this work. So that is the motivation and contribution of this work. For the rest of the presentation, the outline is as follows. We start off by looking at the first application class, tensor solvers, looking at the initial, let's say, primitive design for FPGAs, then detailing the challenges and optimization we encountered when using SYCL. We also briefly point out the development of performance models for these applications, but we ask you to refer to the paper for more details on this. Next, we move on to our second class of application, multidimensional tridiagonal system solvers, where we briefly note the different algorithms for direct solution of tridiagonal systems and establish how high throughput multidimensional solvers can be created using popular Thomas algorithm. We also discussed challenges on implementing it on FPGA, mainly leading to the optimization to reduce the on-chip memory consumption of the Thomas solver. After that, we look at the performance from the designs on Intel FPGA and compare it to the same application implemented on NVIDIA V100. Performance is compared in terms of runtime, bandwidth, energy, and energy consumption. Finally, we will note some key lessons learned and conclusion from this work. Stencil computations are quite well understood. We see following general setup in these applications. In this stencil loop, we are going to update all the values in the time step t plus 1 using this expression. This expression requires 5 points which are specified using this cross stencil, and we are going to multiply those mesh points with constants k1 to k5, and this expression can be elevated and mesh point at xy coordinates can be updated for the time step t plus 1. We can see that all mesh points in time step t plus 1 could be updated in parallel as there's no dependency in this expression. This kind of scheme is called as explicit numerical solvers. This is a naturally parallel algorithm suitable for implementation on FPGAs as well as many coprocessors. These types of stencil loops are commonly used in implementing finite difference method for solving partial differential equations. Next two slides are about how to codify these stencil applications using SYCL, starting with general ND range style kernels. Part of the program executed on SYCL accelerator platform is called as kernel. These kernels will be executed on processing elements of a compute unit. A device usually has multiple compute unit. Instance of program computed on processing element is called as work item. Whole work is divided into work groups and indexed using a global range. Set of work groups specified by the local range is scheduled in a single compute unit for specific optimization such as data reuse using cache. Kernels based on these index ranges are called end-range kernels. It is a popular GPU programming style supported by SYCL, but this kind of implementation leads to poor performance on FPGAs. This is because these kernels implementation mainly depend on lower global memory bandwidth of FPGA, and kernel-to-kernel communication using pipe is not possible. Moreover, design requires a multi-port cache for data reuse. However, required cache size is unknown and access pattern is not explicitly defined at compile time. On the other hand, single task kernel structure provides the compiler more information to get optimized circuit implementation. Here we declare a fixed size of array which can be mapped to on-chip memory. Variables declared in this code will be mapped to registers. Single task kernels are usually loop based, and Intel offers many attributes and pragmas to be applied to these loops. In each iteration of the loop, data move through part of the code in the blue circle, which is mapped to window buffer in circuit using on-chip memory and registers. Here we make sure that points specified by the stencil appears in the registers in mapped circuit. Stencil computation expression in the red rectangular box will be mapped to detailed circuit using DSP units. This is a kind of primitive design for stencil applications, but the optimizations are on following slides. The primitive design we have seen updates a mesh point with each clock cycle, but we can also update two or more mesh points in parallel as there's no dependency, and this method is named as self-parallel method in work by Vaidya Surya et al. Here the difference is we input, compute, and output. We factor number of elements in each cycle. In this diagram, it is 2. Since we input many elements in single clock, it demands more off-chip memory bandwidth. Yet, the number of elements need to be buffered is same, hence no additional requirement for on-chip memory. In SYCL, we have to create a wider data path using struct, which consists of number of array elements. Pragma is used to vectorize the stencil computation. Here we do another optimization separating off-chip memory operation and computations. This allows to have separate kernels for memory read access, stencil computation, and memory write access. Data moves from kernel to kernel through SYCL pipes and Intel extension. Instead of feeding output of compute kernel to write kernel, we can feed compute kernel output to another compute kernel, as in this block diagram. Here, two iterations are computed in parallel. This is called as step parallel method in work by Y.J. Surya et al., or commonly called as unrolling iterative loop. The diagram shows this circuit to be replicated. Hence, resource consumption is proportional to number of compute kernels. Usually, previously seen self-parallel method and this step parallel method are combined to get best performance on FPGAs. When it comes to codify using SYCL, we use template specialization to unroll iterative loop. We note that even though kernel names are optional in SYCL 2020, here it is required as we need to differentiate the kernel instantiation to connect the SYCL pipes. This is also achieved through template-based implementation. Let's look at optimization for smaller meshes. This diagram shows the latency between pipe input and pipe output, as certain number of mesh elements need to be buffered to get first output. The delay will get added up when unrolling the iterative loop, leading to significant latency for meshes with smaller heights. The diagram shows the latency for processing two block of iterations for two meshes. Here we see for each mesh, the compute kernel 1 is idle for a significant amount of time, as data needs to be go through other compute modules and needs to be written before starting the next iteration. Instead, in batch computing, where meshes are placed one after another, compute kernel 1 can start processing the second mesh immediately after finishing the first one. This will reduce the idling time of the compute module as well as improve the average latency per mesh, as visible in this diagram. And here we note that there's no SYCL specific construct required to apply this optimization. Let's see a special optimization required when codifying stencil application using SYCL. We have seen that batching will reduce the pipeline latency overhead for smaller meshes, but kernel job sufficient overhead will dominate if overall kernel execution time is not large enough. This diagram shows the execution of application on FPGA through job sufficiency. Since we have to swap the memory locations after each iterations, cost has to wait until queue is empty, and after that it will submit the jobs for the next iteration to the queue. This leads to additional overhead. Solution can be attempted by moving iterative loop to each kernels as outer loop. In this attempt, read and write kernel will require both buffers A and B. In SYCL, runtime manages the kernel schedules by dependency analysis, and here read kernel to be scheduled after the completion of write kernel. However, write kernel completion is possible only when read kernel provides all the data, leading to deadlock in this case. Here we note that in Chinese FPGAs, all three kernels can be implemented in single kernel as a function calls, because Chinese toolchain for C++ for Vivado supports data flow optimization across many loops and functions. Solution to avoid deadlock by runtime scheduling is to fuse the read kernel and write kernel. Following SYCL code segment shows fused kernel. Here, the key part is the delaying the pipe rate, as in the blue box. This is because pipe operations are blocking operations. If data is not available at the time pipe read is attempted, it could lead to deadlock or reduced throughput. Let's see how we can calculate the delay value. It requires the understanding on how loop operations are scheduled on FPGA. This diagram shows the clocks at which first pipe read and write are attempted. Next attempt will be 1 clock after the schedule, and it goes like this. This schedule information can be obtained from Intel Schedule Viewer of generated report. Other determining factors of the delay value are the pipeline stages and delay buffers. This diagram shows simple delay model of read-write kernel connected to compute kernel pipelines. Here, first pipe write and pipe read are scheduled at clock WR and clock RD. There are two kinds of delay elements: pipeline stages and delay buffers. Apart from adding latency, delay buffer requires certain number of elements to be buffered to get first output. This expression is for stall-free data flow. It makes sure that data is available when pipe pop is attempted by adding all the latencies. And this second expression is for deadlock avoidance. Here it makes sure that delay buffer is filled before the first pop is attempted. And this last expression is for the deadlock stage. Here delay buffer is not filled before the first pop attempted, or like pop is attempted before first push to the pipe. Let's look at predicting the performance of stencil applications. Latency in processing a batch of mesh is mainly due to looping through the mesh points and latency in delay buffers and pipeline stages. Diagram shows the clock spent in looping through the mesh points in using black dots, and delay due to the delay buffers using the red dots. We note that delay buffer latency will add up if there is multiple compute kernels, and it is similar for the register stages. Let's briefly model the latency in processing measures of batch size B for n iterations. Other parameters are vectorization factor V, iterated loop unroll factor P, stencil order D, and mesh dimensions are M and L. The first expression, which calculates the total delay, adds the pipeline stage delay and the delay buffer delay. Pipeline stage delay can be calculated by summing a difference between the pipe write and pipe read clocks. Delay buffer delay can be calculated by dividing the number of mesh points need to be buffered by the B number of mesh points being pushed each clock cycle. And finally, the total latency can be calculated by adding the latency to loop through the mesh points. Similar model can be developed for the 3D applications, and it is on the paper. And over 85% of accuracy is obtained for both models. Okay, I am going to the next part of the presentation, multidimensional tridiagonal system solvers. Tridiagonal systems are common when attempting to solve partial differential equations using implicit numerical schemes. Popular applications domains are computational fluid applications and financial computing applications. Structure of tridiagonal system matrix is in this figure. Here unknowns u0 to un-1 need to be computed. Common tridiagonal system solvers are Thomas algorithm, parallel cyclic reduction or PCR, and SYCL algorithm. Popular alternating regression implicit methods solve multiple tridiagonal systems along coordinates of the multidimensional mesh. Here, the figure illustrates for a 3D case. Our previous work to be published at ICS 2022 has shown Thomas algorithm is efficient on FPGA when there is a need to solve multiple tridiagonal systems. Thomas algorithm is given here. It has dependency between loop iterations as well as between two loops. Circuit diagram represents the dependency when updating the value Ci, and it depends on the previously calculated value Ci minus 1. Multi-clock cycle floating point multiplication, division, and subtraction operation with feedback path leads to higher latency sequential loop iterations. If the loop iteration latency for the forward loop is LF and backward loop is LB, then the total iteration is N into LF plus LB. Latency of the forward loop and backward loops add up due to sequential operations as in this figure. We have seen there is a dependency between loop iteration, and the circuit will be ideal for significant clocks. If we have multiple tridiagonal systems to be solved as a group, then we can interleave the computation in order to fully utilize the arithmetic circuit pipeline. Here we note that number of systems need to be interleaved should be higher than arithmetic pipeline latency LF or LB. We can have different group size for forward loop and backward loop, but to make the model simple, we are making group size G maximum of LF and LB. Average clock cycle spent on each system for each loop will be N. Here N is the system size, but the latency for the single system will remain same. In order to execute circuit for the forward loop and backward loop in parallel, we will need multiple group of system. Each loop will execute different groups of in parallel in a ping pong manner as in this diagram. Ping pong buffer design will require dual port memory with separate read and write locations, which doubles the memory requirement. On-chip memory is key and limiting resource when trying to solve larger systems. Figure shows the kernels to implement this Sommers solver. We assume systems come sequentially one after another through the pipes. Hence, it requires the additional kernel named as interleaving system, which requires storage for data structures A, B, C, D. Forward solve requires storage for C star and D star, and backward solve requires the storage for Joule. Each data structure will require 2 times G times n words, in total 14 GN words. If all kernels use the same group size G, twice memory requirement is due to the ping pong power setup. Let's look at an optimization to save on-chip memory. In subset of implicit applications, we can internally generate coefficient. In that case, coefficient generation can be fused with forward solve kernel to save storage required for the coefficient ABC in interleaving system kernels. This will save 49% of on-chip memory based on group size for target Intel FPGA D5005. Forward solve requires significantly larger group size because of slow floating point division operation, which is not natively supported on Intel FPGAs. Since storages for D, C star, D star require same group size, we can save on-chip memory by having smaller group size. For that, we decouple our computation in this red box of Thomas forward solver to another kernel called as R generator. This leads to storage for another data structure R, but group size for other data structures will be much smaller. This reduces the memory requirement by 40% compared to the fused version. We apply the SYCL-based workflow developed for the Intel FPGAs to two representative applications. First one is RTM forward for explicit case. It is a 3D 25-point stencil application on vector elements. Other one is 2D heat diffusion application using alternating direction implicit method. Both applications use single precision operations. Target platforms for this experiment are Intel PAC D5005 FPGA and NVIDIA V100 GPU. Specifications for the both platforms are in this table. Here we note that GPU's bandwidth is more than 1 magnitude higher than FPGAs, and its theoretical computing power is also higher than FPGA. FPGA kernels are implemented using Intel implementation of SYCL, data parallel C++. We optimally implement same applications on NVIDIA V100 using CUDA. RTM application is implemented using OPS framework. 2D ADA heat diffusion application is implemented using state-of-art tight solver library for multidimensional tridiagonal system solvers. We tested NVIDIA's CubePass, but tight solver library gives equivalent or better performance along SY coordinates. We compare the performance of these two implementations in terms of time to solution, bandwidth, and power. Batching helps to saturate GPU and to do fair comparison as GPU is throughput oriented. Algorithm of RTM application is given in this figure. Here KT, Y, S are vector 3D meshes and rho and mu are scalar 3D meshes. FEML does a 25.8 order stencil operation. FPGA implementation and GPU implementation consist of 4 kernels. We chose structure of array data layout as it gives better performance on GPU. When comparing the runtime, GPU performs better for smaller meshes, but FPGA is closely competitive with GPU for larger mesh configurations. Predicted runtime on FPGA by our models is closely matching with actual runtime, validating our models. When considering the effective bandwidth, FPGA performs slightly better for the larger mesh configuration. When it comes to energy consumption, FPGA saves over 59% of energy spent on GPU. Algorithm for 2D ADA application is in this figure. There are 3 main steps: pre-processing, tridiagonal system solving on SDIM and YDIM. Accumulation step is fused with pre-processing in FPGA kernels and with tried solve in GPU kernels. When comparing the runtime, FPGA performs better than GPU and model predicted runtimes closely matches with actual runtime. Here we note that GPU radon assistant libraries doesn't support coefficient fusion, and we estimate the GPU performance if the optimization is done and it is plotted in dotted red line. We see still FPGA is faster. When considering the bandwidth, GPU YSOL reaches a good bandwidth, but HSOL performs poorly. This is due to local transpose required in GPU implementation as in this figure. For more detailed, refer the work done by Andre et al. But FPGA achieves a good average bandwidth. When considering the energy consumption, FPGA saves more than 76% energy spent on GPU. We can list following as key lessons we have learned. Even though SYCL offers functional portability, significant customization is required to gain decent performance on FPGAs. This includes pipe-based kernel-to-kernel communication and custom memory hierarchy design. These transformations required to gain better performance comes with cost of higher programming overhead compared to programming instruction-based traditional architectures such as CPUs and GPUs. FPGAs could challenge GPUs for similar set of HPC applications, giving competitive or better performance with significant energy saving. We have used SYCL to design and develop structured mesh-based solvers on Intel FPGAs. This included workflow for any stencil solvers and efficient multidimensional tridiagonal system solver based on Thomas solver. Key challenge to get near optimal performance on Intel FPGAs using SYCL are reducing kernel call overhead by moving iterative loop to FPGA and reducing on-chip memory usage by decoupling computation in Thomas forward loop. We applied the workflow on two non-trivial production representative applications and implemented design on Intel D5005 FPGA. FPGA provides competitive or better performance compared to optimized NVIDIA V100 implementation with 59% to 76% energy saving for largest configurations. As next step, we are planning to automatically generate SYCL FPGA target code using DSL and errors later. We are planning to explore the performance on Intel FPGAs with HBM memory as well. We are grateful to the funding bodies that supported this work and to the organization and individual provided resources and advices. Full reference of the works we have cited are listed here. Designs and libraries we developed are open sourced and available in following GitHub repositories. We invite you to read our paper for full details of this work. Thanks for listening.